Okay, in this section, 14.3, 14.4, I actually want to do a couple of problems dealing with implicit rate, differentiation, and related rates. So these two ideas are a little bit more complicated for business calculus students in that there's a little bit more like math involved when you're doing this kind of differentiation. So I want to try to do a problem from each one of these little sections right here. So I want to do one where we take the implicit we do implicit differentiation, and of course then one or a couple where we do related rates. So it's similar. It's like an extension of implicit differentiation, but I'll show you how it works. So let's look at a problem from that first area where they want you to find dy dx, so just the derivative, using implicit differentiation. And of course, a lot of times you use implicit differentiation because your equation is not easily solvable for y. So like, this would be a very difficult equation, 7x cubed equals 5y squared plus 9y. That would be very difficult to isolate the y in. So what we want to do is actually start by taking the derivative of both sides with respect to x too. And a lot of times you see when they do derivative of both sides, they'll have like d dx. That just means take the derivative of that side. Of course, what you do to one side, you're going to have to do to the other side. So we'll take with respect to x, derivative with respect to x, the derivative of the 5y squared plus 9y side as well. Okay. Now on the left side, with the 7x cubed, very easy to take the derivative of 7x cubed. You just use your rules from Unit 2. That'll be 21x squared. So nothing really different there. And of course, when we do the derivative of the right side, you're just going to take the derivative of each part of this. Now, this is what is different, okay? So on that 5y squared, if you're going to take the derivative like it was a normal variable, okay, you would end up getting 10y to the first power, okay, when you take the 2 down 1. But since you're doing with respect to x, and you just took derivative with something that has a variable y in it, okay, you're just going to put beside this, every time you touch something with a y in it, you're just going to put a dy dx. It's kind of like you're just putting this fraction right beside this right here. Now there's a lot more in-depth going on behind the scenes, and if you are interested in learning more like what exactly, why do we put that there, I won't be able to go into that in this video, but it would be a really good idea maybe to follow up with a Kahn Academy video or some kind of explanation why you would do that. So we're going to have a dy dx right there because we took derivative with something, an expression that had y in it. Okay, then I'm going to go over here to the 9y. Okay, when you do the derivative of 9y, it just gives you 9. But since it was a expression that had y in it, I'm going to have to put this dy dx thing beside it. Now, this is technically your derivative of the original equation, although they do want you in your homework system a lot of times to solve for dy over dx, so we need to isolate that to one side. So this is what I'm going to do now on this left side, or on this right side. I'm going to factor out dy dx, so just kind of treat it like a normal variable basically when you do these problems. So dy dx. Okay, I'm going to factor that out. And then here's what we got. 21x to the second equals, and then 10y plus 9, and then you're times it by that dy dx. And you only have one more step left to do to finish this one out. Just divide both sides by 10y plus 9. So basically just divide off this 10y plus 9, and on the left, yeah, you'll have 10y plus 9 on the denominator. So your final answer will be something like this right here. Okay, dy dx equals 21x squared divided by 10y plus 9. So you see you have a y in your derivative expression, which normally we don't have that, but in this case we do. Okay, next off, I want to look at a problem similar to number 8 on your homework, and this is where they start getting into related rates, where you have x and y being functions of t. Okay, so in these problems, when you do the derivative, you're actually going to do the derivative with respect to t and not x. And since you do it with respect to t, you are actually going to have to put a dy dt whenever you do a derivative with y, and a dx dt whenever you do a derivative with something with x. Okay, so what we want to look at here for this first problem, they give us the equation y cubed equals 2x squared plus 6y. So what I want to do is start by taking the derivative with respect to t on both sides. So derivative with respect to t, I'm just going to actually write that d dt and then of the left side, okay, and then I want to do derivative with respect to t d dt of the right side here, okay. The right side of the 2x squared plus 6, okay? And then when I take the derivative of each one of these, okay, so this will be 3y squared, just use your basic derivatives. But since I was doing with respect to t and not with respect to y, I'm going to have to add in this extra dy dt kind of fraction beside this, okay? Next, I'm going to go to the right side and do derivative of 2x squared, which will be 4x, okay? And then I'm going to have dx dt, since I was doing with respect to t and not x. Okay, same thing for the 6. Well, the 6 actually becomes 0, so when you do derivative of just 6, it just becomes 0. So there's nothing right there. And this will be our starting derivative. Now, this one actually wants us to get a value for dy dt. So we have to solve for dy dt on this one. And they give us actually values in the given statement of dx dt is 4, x equals 1, and y equals 2. So actually now you can just plug in all of your values. So plug in what you know, okay, and you'll have 3 and then 2 squared times dy dt is what I want to solve for. So I'm just leave that there. 4x is equal to 1, and then dx dt, the rate of change of x with respect to time, is 4. Okay, I'm going to do some simplification right here, okay, and you'll get 12 times dy dt equals 16. Divide both sides by 12, and you'll get what dy dt equals 16 over 12 reduces to 4/3, and that'll be your answer that they want you to put in for this problem. Okay, the last type of problem that I want to do is one like number 10 on your homework assignment, and this is one where you have like revenue, cost, and profit, and they actually want you to find the rate of change of revenue and cost and profit with respect to time. So they're actually wanting you to find like dr dt for each of these types of problems. So let's look at the revenue one first, since it comes up first. And actually, if we find revenue and we find the cost dr or dc dt, we can actually find the profit dp dt just by subtracting cost from revenue. But first, the revenue one. They give us an equation of 60x minus 0.5x squared as the revenue equation. So what I'm going to write, instead of the r of x, I'm just going to write r equals, and then 60x minus 0.5x squared, like that. Okay. Now, what I want to do here is take the derivative with respect to time. So d dt of both sides, okay, right here. And when you do it on the left side, you're taking the derivative of r, just the variable r. That would just end up being 1, if you had it. But since you're doing, since it's r and not t, you have to put dr dt there. Now, this is actually what we're trying to find. Dr dt is the what we're trying to actually find for an answer, like the rate of change with revenue with respect to time. So we're going to leave that there. Now, 60x. Derivative of 60x is just 60, but since it's a variable x and not a variable t, we are going to have to insert a dx dt function right beside the 60. Okay, and then over here, 0.5x squared, taking the derivative of that, well, this is going to end up being minus 1.0 x, but since it's x and not t, we're going to have to do dx dt right there. Now, on this type of problem right here, we're not going to have to isolate dx dt or anything like that, because they actually give us values for x, the number of units produced, and they give us a value for the rate of change of units per day. That's the dx dt. So actually, I'm just going to plug in what I know here and then simplify a little bit to get our final answer. dxdt, that was the 15 units per day, minus 1.0. We're doing 25 units. And then dxdt is that 15 again right there. And then I just want to simplify that a little bit. And I get 525. And this is revenue per day, so it's $1 per amount per day. And that's the rate of change of revenue with respect to time right there. Okay. And now you'll do cost as well. Very similar way. And then once you get revenue and cost, of course, you can subtract those two to get profit. So cost, they give us a cost equation of 4x plus 20. So that's our cost equation. So I'm just going to write C equals 4x plus 20. And then I want to do the derivative with respect to time of both sides. So dt of both sides, basically. Okay, this will give us dt over here, derivative of cost with respect to time. And then 4x, derivative of 4x is just 4. But since it's x variable and not t variable, we will have to put in beside this dx dt. Okay, plus, and then derivative of 20 is just 0, so you don't have to put anything there. So the change of cost with respect to time will be 4, and then dx dt is 15 right there, which is 60. It's a cost per day, so $60 per day will be our dc dt. Okay, and then last but not least, the only thing you really have to do to find profit, if you remember, profit profit equals revenue minus cost. Well, dp dt will be dr dt minus dc dt, which we know dr dt is the 525 minus the 60 will end up giving you the change of profit per day, which will end up being your $465 per day. That's your rate of change. That's dp dt, the change in profit per day. Okay, so they're shooting you some different examples of related rates and implicit differentiation.